Saritha Kumari, Assistant Professor, EEE Department, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. The course today I'm going to give the lecture. The course is Performance of Transmission Lines and Cables. Previously, as I mentioned, my last lecture also, the previous lectures in the course Transmission Lines. Under that, I have given with the course title Electrical Power Transmission Lines. So the slight change in the course title. So, but everything is same, only slight change in the course title. So, Performance of Transmission Lines and Cables. So, today the topic is problems on medium transmission lines. So, it is mapped to course outcome 3. So, the problem, nominal-π method using the problem is given nominal-π method. So, basically, in my last lecture, I explained about the medium transmission lines to estimate the performance using 3 methods. End condenser method, nominal-t method, nominal-π method. So, now the problem is based on nominal-π method. So, problem using nominal-π method, find the sending end voltage and voltage regulation of 250 km for 3-phase 50 Hz transmission line delivering 25 MVA at 0.8 lagging power factor to a balanced load of 132 kV. Given 3-phase line and the method given is nominal-π method. So 3-phase line and system length is given to 50 kilometers. So clearly they mentioned the method also. What is a method to solve this problem? So nominal-π method. So and they have given transmission line delivering parameters. That means the load side, receiving end parameters are given. The power is given 25 MVA and power factor is 0.8 and 0.8 power factor lagging and balanced load 1. So operating voltage VR is given 132 kV. Now the line conductors are spaced symmetrically 3 meters apart and the conductor resistance is given 0.11 ohm per kilometer and its effective diameter is 1.6 centimeter. Neglect leakage. So they have not given in this problem line inductance and capacitance directly, but they have given the spacing between the conductors, that is given 3 meters and conductor diameter is given 1.6 centimeter. Resistance is given 0.11 ohm per kilometer. So here to find the sending end voltage, what they asked here, sending end voltage and voltage regulation. So first using given data, calculating the line inductance and capacitance. So previously we know to calculate the transmission line inductance for a 3-phase line, line inductance and line capacitance. So the formula we need to recollect here because inductance, capacitance not given in the problem directly. So line inductance. So first here it is shown calculating line inductance L. Okay. So I hope you are able to recollect. So the line inductance per, okay, this is per conductor. Okay, the line inductance is 2 into 10 power minus 7 log base C D by R dash. This is Henry per meter. So this is the basic actual expression for inductance. Okay, inductance per conductor in a transmission line is given by 2 into 10 power minus 7 log base C capital D by R dash. In this, capital D represents the spacing between the conductors and R dash is the effective radius of the conductor, which is given by 0.7788 into R. Okay, where R is the radius of the conductor. Now, the same expression is simplified, written this log base C in terms of logarithm base 10. It becomes whatever we see here, 0.461 log base 10 d by r dash. So the same expression in terms of log 10, log base 10, it becomes like this 0.461. Okay, if we simplified the same expression, simplified, it becomes, that is what it is used here. So 0.461 log base 10 capital D by R dash. So substituted here, what is capital D spacing between the conductors given? 3 meters. Okay, so meters, and effective radius is R dash 0.7788 into what is the radius? Given diameter 1.6, so radius becomes 0.8, right? 0.8 centimeter. So this is 0.8 centimeter and the distance is 3 meters. So this one also substituted in centimeters. So both in numerator and denominator. So that's same units. So the value of L becomes 1.24 millihenry per kilometer. Now capacitance. Capacitance expression the similar manner we recollect capacitance also. For a transmission line, the capacitance from the previous lectures. So it is given by 4 pi epsilon. Sorry, it is given by 2 pi epsilon naught log base C d by r dash. So substituted epsilon 8.854 into 10 power minus 12, and this log base C is converted into log base 10. The same expression becomes 0.242, 0.0242 by log base 10 d by r dash. 0.0242 by log base 10 capital D by, it is only R, not R dash. Okay, in capacitance, they take only the radius. Okay, there is no effective radius concept. So that's why it is log base 10 D by R, capital D by R. So substitute the parameters again. D is 300, radius is 0.8. Finally, capacitance is given 0.0094 microfarad per kilometer. Okay, so and also know that in this expression, this is the expression 0.461. Okay, for inductance it is for millihenry. Inductance value gives in millihenry per kilometer. Similarly, C expression 0.0242 by log base D by R expression gives C value in microfarads per kilometer. Okay, that is how this, the derived expression is considered. Okay, now radius is directly given, radius conductor radius 0.11 ohm per kilometer. Now we have to take the line parameters with respect to the total length. So the total length of the line is 250 kilometers. So calculated resistance 0.11 into 250. So that is 27.5 ohm. Next, calculating X. Okay, X is nothing but line reactance, because only we know L value, calculated L value. X is 2 pi FL. So give a system line operating frequency 50. So L is substituted 1.24 into 10 power minus 3, and also with respect to the total length of the line. Okay. So finally this is a value of X. Next, Z is calculated R plus JX 27.5 plus J 97.4, that is given in polar coordinates. Okay. Now Y, calculating Y, line admittance, because in nominal-π method we know we require both Z along with Z, we require Y also. Y is calculated based on C value. So here what is Y? J omega C, because with respect to the total length it becomes J omega C L. So J omega is nothing but 2 pi f, right? So 2 pi f 50 gives 340, and C value is calculated 0.0094 into 10 power minus 6, and L length of the line is 250. So J means at an angle of 90 degrees, right? J operator means an angle of 90 degrees. So finally Y value is obtained as 7.38 into 10 power minus 4 at an angle of 90 degrees more. Now here I value, because based on the load parameters given, load parameters what they have given, load power is given, uh, 25 MVA, and voltage is given 132 kV and power factor 0.8 lagging. So because in using that data we can calculate current line, receiving and current. So that is given by, so the power expression, this is a power expression, P is equal to, for a three phase line, root 3 VR IR cos phi. We want IR, right? So IR becomes P by root 3 V cos phi. So here power is nothing but, so IR is, what is IR? P by root 3 VR cos phi. So here the power is given not in watts, it is given in MVA. So that means they have given P by cos phi value. Okay, the reactive power is given, that is the meaning. So that's why this becomes directly IR calculation in P by cos phi, it is substituted MVA rating of the load, that is 25 MVA. So 25 into 10 power 6 divided by root 3 to 132. What is the receiving voltage? 132 to 10 cube. So 10 cube, numerator, denominator gets cancelled. So in numerator we have only 1000. Okay, so and power and here the angle, because always we know that the receiving end voltage is taken as a reference. Then IR is mentioned, given its value along with the angle. Okay, so that's why IR is calculated 25 into 1000 by root 3 into 132. Magnitude is calculated, which is given as 109.3. And because it is with respect to the power factor, the current receiving and current must have the angle. Okay, okay, so that's why it is given 0.8 power factor lagging means minus 36.9. 0.8 power factor lagging means minus. Okay, so that is how IR is calculated. Okay, now line parameters are calculated in terms of Z and Y. Okay, so we substitute here to calculate the Vs. So that is what asked in the question. So first, receiving in voltage. So for a nominal-π method, we know that, right? Nominal-π method, this is the equivalent circuit. So this is a Z, this is Y by 2. This is, okay, this is nominal-π. So here Vs is given by, okay, Vs is given by VR plus, okay, the drop in the line. So of course we can't say directly how the drop in the line it is. We need to remember the equations, nominal-π method, okay, the equations for Vs and Is. So better remember in terms of matrix form. 1 plus Yz by 2 into Z. This is Y, 1 plus Yz by 4, 1 plus Yz by 2, VR, IR. So this is a, okay, this is how we can remember easily the equations of Vs and Is. So Vs equation is 1 plus Yz by 2 into VR plus Z IR. Okay. So now, so substituting all the values. Okay. So now, so here look at here. So here 1 plus half into Y is what already we calculated its value. Okay. So this is 7.38 into 10 power minus 4 at an angle of 90 degrees. Z is 1.2 at an angle 74. 2 and VR is calculated, substituted per phase value. Okay, per phase value 132 by root 3 means 76.2 kilovolts. Okay, so it is substituted in kilovolts only. So next ZIR also we need to substitute in kilos, value in kilos. Okay, So here see, this is Z value, this is Z 101 at an angle 74. Next, IR is written 109.3 into 10 power minus 3. Why? Because we want to substitute the value this second term also in kilovolts. That's why it is written 10 power minus 3. IR at an angle of minus 36.9. So finally, it is simplified and obtained Vs value 82.2 plus J 7.48. So in polar form, this is the value. So Vs per phase value is sending end voltage per phase value 82.6. 82.6 at an angle its angle is 5.2 degrees. So that is a per phase value and it's a line value finally calculated root 3 into that 82.6, which is obtained as 143 kV. Okay, so that is the value of Vs. So Vs is 143 kilovolts obtained calculated. Given what is the receiving end voltage, operating three phase voltage 132 kV. So they are almost, they are not much difference. Okay, that is how Vs and Vs calculated. Then in a given question, they also ask you to calculate regulation. So that is calculated. So we know that what is regulation formula. Okay, difference of directly we can calculate regulation, transmission line regulation, Vs minus Vr by Vr into 100% regulation. So this is a formula to calculate regulation in case of transmission line. But to calculate the exact value, this is a formula. Okay. So what is that to calculate? So this percentage regulation, they also say it as receiving end voltage at no load. Okay. Minus receiving end voltage at full load by receiving end voltage at full load. So that is the exact formula. Receiving end difference of the receiving end voltage at no load. Okay, minus receiving end voltage at full load by receiving end voltage at full load. So here how they calculate receiving end voltage at no load? This is how. Okay. That is calculated Vs by 1 plus Yz by 2. Okay. So that is how calculated and substituted. Okay. So it is obtained as, this is 132. So obtained as 12.3. So calculate regulation, this method also gives the almost the same answer. Okay. There is not much, there is no much difference actually. So as I said, this is a formula, but exact formula for regulation is in case of transmission line. This is a exact formula. Okay, this is a problem. One more problem. A single phase overhead transmission line delivers 1100 kilowatt at 33 kV at 0.8 power factor lagging. The total resistance, inductive reactance of the line 10 ohm and 15 ohm respectively. Determine first bit sending in voltage, second sending in power factor, transmission. So here it is given single phase line. Load parameters are given same manner like previous problem. Line R and L values are directly given. So it is not given a specific medium operating voltage. Okay, medium line or a particular method. So it is not given. So then we go the first method, that is looking at the line parameters, because R and L values are given. We go for the direct formula to calculate sending end voltage. How to calculate sending end voltage? Receiving end voltage plus drop in the line. Okay. Receiving end voltage plus drop in the line. So like it is. So Vs is given by Vr plus drop in the line. Okay. Okay, now writing first write down the given parameters and calculate current at the load, that is receiving end current. So here calculating receiving end voltage. So these are given data, and line current, that means receiving end current is given by what is for it, transmission line, we know that single phase line. This is a power expression. So current is given by P by V cos pi. So at the receiving end, so 1100 into 10 cube by 33,000 into 0.8. Okay, so power factor is given 0.8. So that is written separately. Okay, so if you want to mention here also we can write up minus 36.9 degrees. So first bit, calculating sending end voltage. So VR is reference. So IR is what? So as we already know, that is 41.67 at an angle of minus 36.9 degree. So if we write down in rectangular form, this is the value. Okay, 33.33 minus J 225. Okay, so like in terms of cosine and like this also you can show. Now, Vs is given by substituting the values. What is VR? 33 kV means 33,000 plus I value, okay, I and Z. This is what is Z line resistor R plus Jx, right? So, which is directly given. So, simplified using calculator, scientific calculator, and obtain Vs is, okay, its magnitude. Okay, of course, this is a rectangular form. Converting that into polar form gives its magnitude as well as the angle. Magnitude is 33,709. And a second bit, what they ask, calculate the sending end power factor. Sending end power factor, cos pi s. They ask cos pi s. So, from the previous slide, we know that so cos pi s means angle between Vs and Is, right? So here this is a Vs, right? And here Is and Ir are same, right? In the transmission line, using given it is a direct line. Okay, there are no parallel paths. So whatever the line current, whatever the only one current present, which is a receiving end current as well as sending end current. So pi s is to calculate pi s, angle between, okay, I, already what is the first current present? Load current, that is receiving end current, which is here, right? So to calculate angle between this I and Vs, that is given by, from this phasor diagram, pi r plus alpha. What is alpha? It is taken angle between Vr and Vs. Angle between Vr and Vs. So first already pi r is known. Pi r is known. Okay, minus 36.9. Now calculating alpha. So alpha is given by from that vector diagram. Okay, from that vector diagram. Okay, what is a z? Okay, so that is nothing but tan. Okay, alpha is given by tan inverse of 250 by, okay, 250 by it is taken tan alpha, right? So tan alpha means what it will be? Tan alpha means it is given as, okay, Iz by Vr. Vr is how much? 33,000, right? Okay, Iz, this is Iz. Okay, so Iz they calculated. Okay, so that it has a magnitude of 250. It has a magnitude of 250. Okay, of course, if it is not clear, we can write cos alpha also. Why? Because Vs is known. Already it is calculated. Vs magnitude 33,709. Okay, whatever it may be, cos alpha or tan alpha. Okay, we will get the same angle alpha. Answer will be, alpha value will be same. Okay, so 0.42 degrees. So now, as I said, what is pi s? From the vector diagram, pi r plus alpha. So 36.8 plus 0.42. So this is 37 point. So sending in power factor, that means cos pi s. Okay, so that is a value calculate 0.79 lakh. Now what is that? What else? The third bit they ask efficiency, line efficiency. So in case of transmission, okay, we know that what is efficiency? Output power by input power. Okay, power delivered by power input. So how do you calculate power output? Already given at the load end. What is the power? It is given 1100 kilowatt. Input is given by output plus losses, right? So input, losses is in the single phase line, right? So I square R. So substituted I and R value, it is obtained as this much. So finally, this is how calculated the value, and this is also another method to calculate the Vs and cos pi s. Okay, so approximate another expression they use, Vs is equal to Vr plus Ir cos pi plus Ixl sin pi s pi r. Sorry. So anyway, this is a solution, and these are the two reference textbooks from the problems where I have taken. Okay, CL Wadhwa, Electrical Power Systems, New Age Publications. Second one, VK Mehta, Rohit Mehta, Principles of Power Systems, Chand Publications. Okay, that's all for this lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.